For you guys for I've been summoned to to basically quickly come up with an expanded version of my CogSci talk to fill this slot. So I wasn't aware of this workshop before, so I'm really glad. It seems incredibly relevant. Okay, yeah. So this is a collaboration between the what was it? Anyway? Between the Computational Cognitive Science Lab at Princeton, the Griffith Lab, and the Computational Urge Perception Group at MPI for Empirical Aesthetics. And yeah, so let's start. So let's start from like a sort of a hypothetical scenario. It is, I already say it's very simplistic, but it will capture some aspect of what I'm going to talk about. So imagine the scenario where you're a cognitive scientist and you're interested in studying the perceptual representations of some newly discovered alien species. And someone calls you and say, listen, sorry, the only thing you have access to is this like huge data set of text. And the question is, what can you do? How much of the perceptual world of that species can you recover just based on text? And as I said, this is very simplistic, but it captures the question that I'm going to focus on, which is how much of the perceptual world can be recovered from language. And recent research gives us hints on the kind of extent of how much information language contains about perceptions. Actually, last year, there was this beautiful talk by Kim and colleagues who showed that, for example, congenitally blind individuals who never had direct experience of colors have actually an in-depth understanding of color concepts. We also did some research on cross-modal alignment, sort of another route towards asking questions in this domain. And we showed that you can predict human sensory judgments very well based on text data. And I will elaborate on this in a second. And yeah, so the trivial thing, of course, is that there's been this tremendous advances in large language models and multimodal models, and you can just write your favorite prompt and get these extremely intuitive, nice images, for example, in the case of DALL-E 2, and so on and so forth. Because this is a more sort of a technical workshop, I'm going to zoom in a little bit on these items just to show you the kind of sort of a preliminary or like the first phase of this research enterprise. And so what we did, or the question that we asked, is to what extent we can predict people's sensory judgments based on the text descriptions that these people spontaneously write when they observe stimuli. So imagine, for example, you look at somebody gives you a set of images, natural images, and you basically have a tool to mine all the tags or textual free text descriptions that people just spontaneously come up with when they observe these stimuli. So one thing that we did here is that we basically came up with this adaptive online paradigm where people look at images, write tags that think they describe the images. And the crucial thing was that we had other people rate the quality of these tags. So people would say in iteration 2, oh, this is really bad. This is not a tomatillo. And a third person would say, here's another proposal, and so on and so forth. And by running this process, we were able to create these highly rich maps. So for example, in this case, in ODA, data sets of emotional prosody, or in this case, in the case of everyday activity video clips. And what we showed is that you can actually predict very well humans' sensory judgments, specifically similarity judgment. So you show them two stimuli and ask them to compare them. And if you use the text descriptions and embed them in your favorite word embedding model at that time, or a language model, then you can do a pretty good job and you get pretty close to the inter-rater reliability. And actually, the interesting thing is that, sorry, I need to minimize this. The interesting thing is that actually you outperform many domain-specific deep neural networks. So it's kind of, for us, that was something that was kind of pretty exciting. So that's just like a really quick tour through sort of what led us to starting to think about this question. And let me now go back to the original debating question, which is how much of the perceptual world can be recovered from language? And let's unpack this question a little bit more. And one of the main challenges here is to come up with a way to quantify the psychophysical content of language. So what does it mean to extract psychophysical content or judgments that are measurable from language? And the key idea in this talk is that we can use large language models as some kind of a lower bound on the amount of information that can be extracted from language. And I say lower bound because language, of course, is mediated through not only through text. People, talk. It's a much more complicated object. But if we focus for a moment on, if you use these language models that are trained on a substantial chunk of human language, we can ask, okay, what at least can we extract out of this text data? And to make it even more concrete, the idea that we had is that what if we can actually, use the powerful prompt comprehension capabilities of these models to just elicit perceptual judgments from GPT models as some kind of a proxy to human language. And so let's make this more concrete. So perceptual, what do I mean in this case by perceptual judgments? Let's go back again to this domain of colors. So, the cognitive toolbox has a lot of techniques for quantifying or characterizing representations. And I'm going to focus on two types of these in this talk that we considered. So in the case of colors, we can look at similarity judgments, and we can look at another paradigm, which is color naming. So let me just give a little review of these two approaches. So in the case of similarity judgments, the idea is that given a set of colors, we can ask people to simply represent them with a pair, and we ask them, tell me on a scale, say from 0 to 1, where 0 is completely dissimilar, 1 is completely similar, how similar you think these stimuli are. And by covering all possible pairs, you can produce a similarity matrix, and then you apply, for example, something like multidimensional scaling. Classic example of this is the Shepard paper from 1980, and you can recover, for example, the well-known color wheel. And you can do this in many domains, right? So you can do this equally well, for example, in the case of pitch, and you can present different tones with different periodicities or frequencies. You ask people to do the ratings, and in that case, the representation that you get is the pitch spiral, which captures two properties. The first one is some kind of a linear pitch height component, and the other one is this heightened tones that are separated by a 2-to-1 frequency ratio. So f0 and twice f0. So 440 hertz, 880 hertz. And that's the lemma, or the circular component. So that's that. Now, the other domain that we looked at is the color naming domain. And here the idea is that we can basically ask people, we can present people with individual colors. We can ask them to name the colors. And then by doing this systematically on a map of discretized colors, we can carve out which regions people associate with which color categories. And there are different ways, but one way is to do it in 2 stages. In stage 1, you just ask people to spontaneously name 8 basic colors, and different people come up with different terms. All their the judgments that the terms that they come up with, and you organize them based on frequency, and you get starting from very common words like red, blue, yellow, green, and eventually you go to less common color terms. So that's stage 1 of the process. And in stage 2, you take the most common list, the most common subset, say the top 15 basic colors, you shuffle them, and then we ask people to name basically which of these colors, given this color, which of these basic terms are base associated with them. So some colors, people are going to be like, oh, it's everyone, this is green, so high consensus regions, and some other regions, people are going to say, oh, this is blue, this is green, so there's some kind of a transient behavior, which would be category boundary. And so that's sort of the, powering through the perceptual paradigms. And I want to add another thing about this domain, which is the reason we think that it would be cool to sort of apply this technique to GPT or this color naming is that they're well-known cross-linguistic variations. So if we hypothesize that these language models are building their representation based on the textual data, then given the same specification, you should expect to see different cross-cultural variation depending on the language of the prompt that you use. So for example, in English, if you were to show people two shades of blue, so the upper color, the lighter blue, and the lower color, the darker blue, both cases people would say blue, whereas if you were to do this with Russian speakers, then you would get actually two robust categories. So the light blue or Goluboy category and the dark blue, which is the Cine category. Yeah. So now let's talk about the second part of this sort of experiment, which is eliciting these judgments from GPT models. And as sort of Andy's talk very beautifully demonstrated, you can basically pretty much ask these models to give you these kind of judgments, right? So you can say, in the case of colors, literally give the model a little description, and Ilya is our like local expert in coming up with these nice prompts. And so we said to the model, you know, people describe pairs of colors, and the crucial thing is that you need to use some textual specification of the stimulus. So it could be a wavelength, or because, you know, there are a lot of HTML documents that use hex codes, you can use a hex code representation of your color space. In the case of pitch, you can use just the numerical frequency in hertz specification, and so on and so forth. And then you tell the model, you know, how similar are these colors in each pair on a scale from 0 to 1, where 0 is completely dissimilar, 1 is completely similar. You specify color 1, you specify color 2, and you ask the model to provide an answer. And obviously, this is a stochastic answer. It's going to change as a function of iterations, as a function of runs. The other thing that is you don't see here, but turns out to be important, is that you should give the model some sort of an example input-output. So you pick 3 random examples. You tell the model, you know, color 1, this, color 2, this, answer some number. And the reason we do this is we wanted to force the model to give us a numerical answer. So sometimes it just doesn't want to do that. So that's a way to do it. That's the prompt engineering behind it. But anyways, so given this, which is pretty straightforward, you can construct similarity matrices just as you do with humans, and then you can apply your favorite cognitive tool to ask, okay, how does these representations look like? And we did this across a bunch of data sets, and we wanted to do really like cover multiple perceptual domains. We didn't want to rely just on colors. So one data set is colors, which is like just a classic data set, and the description on the GPT side was hex codes. But we also collected our own data to make sure that there is no just like trivial data that exists in the literature. So we covered a 2-octave range of pitch values and collected our own similarity data on it, so it doesn't exist in the literature. And then the queries on the GPT side were frequency in hertz, but you can also look at loudness, so like just loudness in dB units. You can ask about different instrument timbre, so different instrument names, and people on the human data, they listen to actual different instruments. We collected our own data set of vocal consonants. Again, we wanted to create our own data set to make sure there's no just explicit memorization. And you can also do it with taste. So 6 data sets. Likewise, in the case of the color naming, here too, you know, the prompt engineering is really making our life really easy here. So you literally ask the model, you know, name 15 basic colors. It spits out 15 basic colors. And then you use those produced colors to perform the color naming. And you can choose your hex code, and the model will do the naming. And there's naturally going to be some kind of variability in the distribution of the tags or colors that the answers the model chooses. And then you construct your color map and so on. And here we looked at 3 data sets. As I said, there's a motivated reason why we looked at like English and Russian, because there's this predicted documented cross-cultural difference in color representation, in color categorization. And we also compared against some kind of a baseline. So we collected this data online, but we also compared against an existing data set of English color naming in English from Lindsay and Brown 2014. And I should say here that while doing this, we were actually quite surprised how hard it is to come up with like color naming maps in industrialized societies. So this is something to think about. It's kind of interesting. Yeah, so these are the data sets in that case. So now the interesting part. So let's look at the results. So let's start from the similarity judgments. The first thing you can look at is just like how correlated are the model's judgments with the human judgments. So just compute your Pearson correlation. And here on the x-axis, you see the domain. On the y-axis, you see the correlation. And we tried this on GPT-3, GPT-3.5, and GPT-4. And as you can see, in all cases, the judgments were significantly correlated with human data. And the other interesting thing is that although GPT-4 performs on most cases best or close to the top of this case, actually we see that the behavior is, across almost like also GPT-3 is able to perform well. So it's not really that there's something unique about colors, for example. So I think Andy also mentioned this idea of color grounding, image grounding, sorry, that might shape the representation. But interestingly, we see this also across other domains. So there's really something here, it seems to suggest that there's something here about the statistics of the language that the model is using. Okay, so that's cool, but let's look at whether these sort of language model similarity matrices actually capture the fine-grained structure of the representations. So let's look, for example, first at colors. You apply multidimensional scaling on the similarity matrices, and very nicely the model reproduces the color wheel. And so this is what you get from GPT-4, but you get similar results. Slightly noisier, but not that much in the case of the other models. Likewise, in the case of pitch, so remember we said there's this prediction about that when you have frequencies that are separated by a 2-to-1 frequency ratio, you should expect like a spike in similarity. So what you can see here is the x-axis is the separation on a log scale between the first and the second frequency. So it's just 12 times log of f2 divided by f1. And you can see here that, so in this parameterization, which is the semitonal parameterization, 12 is precisely the octave value. And you can see that there is this nice spike that just emerges on top of a generally linear relation. And if you apply multidimensional scaling, you recover the pitch spiral. The last example that I thought was also illuminating is in the case of vocal consonants. So in this case, the language-based GPT MDS, the language-based similarity MDS gives you like a production-based representation, basically that captures the location of production in the vocal tract. So P and B, D and T, M and N, and so on and so forth. Yeah. So that's with respect to, and I have also the MDS for the other domains if people are interested. But let's move on now for the other data. So what you see here, right, is the color maps that you get from online color naming experiments in English and Russian. And the way we produce these maps is by basically looking at, so at each cell is associated with a specific color chip. And then we look at which color category is the most common. And then we color all the cells that are associated with the same tag, the same majority tag, with the average wavelength. And you can see here the maps. And the first thing to notice is that we replicate this nice variation. So let's see what happens now in the case of GPT-4. So you can see the left. Sorry, the right left in Australia is really yeah. So you can see here that first of all, we replicate also in the case of GPT-4 this cross-linguistic variation just by changing the language of the prompt, which is pretty surprising for us that it actually worked. But there are also differences which are pretty interesting. So the first one is that you see that, for example, the turquoise category is much more prominent in these models. And the other interesting difference is the fact that these models are seem to be much more certain about like what is like the consensus color. So the star indicates that, so if there's no star, it means that more than 90% of the people agreed on the same color. If there's a star, it means that between 50% to 90% of people agreed on the consensus color. And you can see that in the case of the GPT model, it's like the model is very certain, even though we used a stochastic, like it was stochastic. Yeah, so that's with respect to that. We also quantified this empirically, like numerically, by computing the adjusted RAND index, which is sort of a clustering measure that counts how many pairs were assigned with the same, consistently with the same cluster, and how many pairs were assigned consistently with different clusters relative to all the possible pairings that you could have, all the possible clustering pairings. And you can see that in both cases, the RAND index between the human data and the GPT data is significant. It's high, so 0 is like completely bad, and 1 is like perfect. And the other encouraging thing is this dashed line, which is basically some kind of an upper bound estimation on how well you can predict, which is we compared our English data against the baseline data of Lindsay and Brown, and there are different techniques. You can see it's about slightly lower than 0.8, and you can see that GPT-4 especially seems to approach that. Yeah, so the take-home message here is that LLMs provide a powerful tool for interrogating the psychophysical content of language, specifically as some kind of a comparison class that we can use to say, okay, if this model is probing language, how far can I go in reproducing, for example? And this is only like one type of an investigation that you could do. So another thing that we looked at is asking the model to provide explanations. So the model gives you some similarity judgment. You can tell it, explain. And I'm showing here just one example, but you can produce word clouds of different, like for all the domains. And the interesting thing is that the model sort of spontaneously seems to pick up on saying, oh, this is a 1-to-2 ratio in the case of an octave, or referring to the term octave, even though nothing in the prompt had to do with that, or strong harmonic relations. So you could look at, this is sort of gives us a way at looking at explanations in the case of perceptual judgments. There are other types of perceptual judgments that people could look at. So for example, like odd one out judgments is a good example that can be easily applicable. And looking at it would be useful, for example, to see how consistent are the representations that you get out of these different techniques, individual differences. So as I said, this model is stochastic. So we looked at mean measures. So we average multiple runs, but you could look at the distribution. Would it capture anything meaningful or not? And also you could look at like non-perceptual domains. So like numbers, I think it's an interesting case. Yeah, and that's pretty much it. Thank you for listening. And I would like to thank my collaborators, Ilya, Paul, Nori, and Tom. Yeah, thank you. How are we doing time-wise?
Yeah, we're perfect on time. Thank you.
Great.
So we have time for a few questions.
Sure. No one's asking, so I will.
Go for it.
So this might reveal just something I don't know about LLMs, but what occurred to me is, the World Color Survey shows these color maps for lots and lots of languages, including ones that presumably there's very little actual text data in.
Mm-hmm.
And so I was wondering, like, the prediction I would make is, of course, that the less data there is, the worse they do, but I don't actually know what the functional form of that is. And I also am not sure at all, is there like shared knowledge from language to language or whatever? So I was just wondering if you considered sort of.
I mean, we are definitely, it's definitely a place where we're expanding now to basically ask how well do these models, how well do they extrapolate or generalize to other less common or less available languages? Absolutely. I mean, I think, isn't it like 50 languages currently that you have in GPT-4?
Yeah. They share a lot of the representation in a way that is exaggerating, is going away from humans. So basically, there is a shared representation across the 50 languages, and we see by collecting the human part of it that is distinct from the cross-cultural variation we see in humans. So basically, a different species is its own way of representing the world that's different, and it's only revealed when we start having multiple languages.
Mm-hmm.
of the similarity for the color one. So is the model, is it really, so the similarity they gave is the similarity between the different color, like how we see the color, or is it like the hex code, the difference, because the hex code it has a string line. Is it string similarity?
Yeah, so yeah, that's a good question. So in this case, I mean, yeah, you cannot present the color itself. So we use hex codes in the case of the color similarity. And you might wonder whether, for example, the model is picking up on something in this representation. And you could do the same thing with like wavelength parameters and see what happens. But I think what's encouraging is that when we do it, for example, with the case of pitch, where the representation was completely numerical. So in theory, if the model was just picking on a linear parameter, you just see like this linear behavior. But we clearly see that it is consistently giving you the spike at a 2-to-1 ratio. So it seems like it is picking on non-trivial relations beyond just simple like string similarity or like linear numerical similarity. Really, you choose your favorite person.
This is also just completely naive, but I didn't realize like where is the data coming from for things like the regardless of whether it's just a string. How was the model string
How was the language model trained? So there was no, so we just used like out of the box GPT model. So we did not train anything here. So it's just consuming whatever is in its training set, which I assume is just includes also stuff like Wikipedia, I guess. But we didn't train anything really. So.
And so in that case, then if it's, because it was really like where did OpenAI get that stuff? But so if that's the case, then how do we know that it's not just finding something in the training data that is? It's not like string based.
I mean, the pitch data is something that we completely collected ourselves. So if there is something, there is no. In fact, I have another paper on pitch representation, which is precisely addressing this problem that there is like people hypothesize about the pitch spiral, but actually, if you look at the data, it's not there. So we actually collected that data across multiple octave range, and so I can tell you certain that this data doesn't exist. Yeah.
I think we can do one more quick question while we set up the next thing.
Yeah.